Have you thought about what lies beyond the edge of the universe? Space is one of the most mysterious things out there, and the James Webb Space Telescope has peered into this abyss and found wonders, from ancient galaxies to the farthest active supermassive black hole ever discovered. It's rewriting our cosmic story. Stick till the end to uncover the secrets that James Webb has revealed. At the very edge of space, the James Webb Space Telescope, a marvel as large as half a 737 aircraft, was humanity's first attempt to capture the universe's first lights. It was built with a budget of around $1 billion and the relentless effort of scientists from NASA, ESA, and CSA over 3 decades. Despite its potential, the telescope has faced hurdles since 1996. This advancement allows it to observe objects that are too faint or distant for Hubble. Operating primarily in the near to mid-infrared spectrum, the telescope can delve into the mysteries of the early universe, studying the first stars, galaxies, and potentially habitable exoplanets. The James Webb Telescope has been peering into the depths of space. It's not just about seeing distant galaxies, but about understanding the origins of the universe. The telescope works like a time machine, taking us back to the early universe. Webb's first year of science has taught us new things about our universe and revealed the capabilities of the telescope to be greater than our expectations. This means future discoveries will be even more amazing. Webb's spectra have confirmed the distances of some of the farthest galaxies ever observed. They have discovered the earliest, most distant supermassive black holes, identified the compositions of planet atmospheres with more detail than ever before, and its observations have resulted in hundreds of scientific papers, answering long-standing questions and raising new ones. The breadth of Webb's science is apparent in its observations of the region of space where the first galaxy formations took place. The telescope has captured the earliest strands of the cosmic web, a vast interconnected structure of galaxies spanning the universe. This cosmic web holds the majority of the cosmos contents, with researchers calculating that it is 5% matter, 27% dark matter, and 68% dark energy. The cosmic web is not just large, it's enormous. It contains up to 2 trillion galaxies, of which we've mapped less than 1%. But why is this important? Mapping the cosmic web promises to answer some of the biggest questions in cosmology. It could reveal what dark matter and dark energy are, how they behave, and whether they change over time. These answers could even reveal the ultimate fate of our universe. However, mapping the cosmic web is challenging. It's invisible, and we can only begin to discern its filaments by spotting galaxies. So, scientists are using unconventional approaches like the principles of origami and spider webs to understand it better. The telescope has found a thread-like arrangement of 10 galaxies that existed just 830 million years after the Big Bang. This structure, spanning 3 million light-years, is anchored by a luminous quasar, a galaxy with an active supermassive black hole at its core. Scientists believe this filament will eventually evolve into a massive cluster of galaxies, similar to the well-known Coma cluster in the nearby universe. This discovery far exceeded expectations. Scientists expected to find something, but not such a long, distinctly thin structure. According to Fig Wang of the University of Arizona in Tucson, the principal investigator of this program, this is one of the earliest filamentary structures ever found associated with a distant quasar. These observations are part of an observation program called ASPIRE, a spectroscopic survey of biased halos in the reionization era. It uses both images and spectra of 25 quasars that existed when the universe was starting to light up after the Dark Ages. The goal is to study the formation of the earliest possible galaxies and the birth of the first black holes. Additionally, the team hopes to understand how the early universe was enriched with heavier elements. The ASPIRE program, aimed at understanding the origin and evolution of the universe, has found that quasars powered by supermassive black holes produce incredible amounts of light and other emissions. These quasars serve as standard candles for distance measurements and studying vast regions of space. At least 8 of the quasars in the ASPIRE study have black holes that formed less than 1 billion years after the Big Bang. These black holes have masses between 600 million and 2 billion times the mass of the Sun. To form these supermassive black holes in such a short time, 2 criteria must be satisfied. First, you need to start growing from a massive seed black hole. Second, This seed needs to accumulate 1,000,000 times more matter at the maximum possible rate for its entire lifetime. These black holes needed a lot of fuel to grow as they did, and their galaxies were also quite massive, which could explain the monster black holes in their hearts. Not only did those black holes suck in a lot of material, but their outflows also affected star formation. Scientists point out that strong winds from black holes can suppress the formation of stars in the host galaxy. Such winds have been observed in the nearby universe but have never been directly observed in the epoch of reionization. How did they get so big so fast? Their existence may tell astronomers something about the overdensities in the infant cosmos. But this is nothing compared to the telescope's discovery about the cosmic ballet of interstellar material. But before that, smash that subscribe button below as hard as an asteroid hitting Earth and keep watching till the end. The James Webb Space Telescope found that black hole seeds need an overdense region filled with galaxies to form. However, only a few galaxy overdensities were found around the earliest supermassive black holes. More observations are needed to explain this. The Aspire program aims to resolve questions about the feedback between galaxy formation and black hole creation in the early universe. This will also reveal more fragments of the universe's cosmic web structure. For the first time, astronomers have detected dark matter hanging from massive filaments that form a cosmic web, trapping galaxies like morning dew on a spiderweb. Dark matter, which makes up an estimated 85% of all matter in the universe, is expected to run along these cosmic web filaments. Despite being invisible because it doesn't interact with light, dark matter dominates the filaments of the cosmic web, forming an invisible scaffold that shapes the universe. However, dark matter does interact with gravity, impacting the movement of everyday matter and light. Using this concept, researchers have detected dark matter on cosmic web filaments threaded throughout the Coma cluster. This was achieved using light from galaxies and stars behind the Coma cluster, along with the high sensitivity, high resolution, and wide field of view of the Subaru telescope's hypersuprime cam. Meanwhile, Sagittarius A*, the supermassive black hole at the center of our Milky Way galaxy, is spinning so fast that it's warping spacetime into an oval shape, similar to an American football. This finding comes from a careful study of radio and X-ray observations. According to Albert Einstein's theory of general relativity, when a massive object is spinning, it can drag spacetime around with it, a phenomenon called frame dragging. The effect is far more pronounced for extremely massive objects like supermassive black holes. The spin rate of Sagittarius A*, which is 4.1 million times the mass of our Sun, has been difficult to pin down. However, a group of astronomers led by Ruth Daly of Penn State University has applied a procedure called the outflow method to measure Sagittarius A*'s angular velocity. This method measures how material is flowing away from a black hole, which can come in the form of a magnetically collimated jet of matter that emits copious radio waves. Hot clumps of plasma, known as plasmoids, are produced in the disk of matter around a black hole and can drift away, radiating in X-rays. These plasmoids form more efficiently when a black hole is spinning rapidly. The team measured the angular velocity of Sagittarius A** to be 60% of the maximum possible value defined by the speed of light. This means the black hole is spinning very fast, warping spacetime into a flattened oval shape. The faster a black hole spins, the more powerful the collimated jets of radiation it emits. These jets can profoundly affect the gas supply for an entire galaxy, influencing how quickly, and even whether, stars can form. Have you ever wondered if the Big Bang was really the beginning of the universe? Recent research suggests a new idea: a cycling universe with repeated bang-bounce cycles. Renowned physicist Brian Cox challenges the concept of something from nothing. Discoveries by the James Webb Telescope add more mystery, raising the question: if not the Big Bang, then what marked the start of the cosmos? Let's explore this intriguing question. Scientists have a good understanding of the early universe through the Big Bang theory. This theory says that a long time ago, the universe was much smaller, hotter, and denser, about 13.8 billion years ago. In a very hot environment, all the elements that make up our world were formed in just about 12 minutes. According to this theory, our entire universe, including stars and galaxies, was once as small as a peach and incredibly hot. Surprisingly, all observations match this fantastic story, making it an accurate description of our early universe. However, there's a missing puzzle piece in our understanding: the earliest moments of the universe itself. The challenge lies in the limitations of our current physics theories. While combining general relativity in high-energy particle physics gives us a framework, it falls short when dealing with the universe's initial moments. The complexity of mathematics reaches a point where our current methods can't provide meaningful solutions. One sign of unexplored territory is the presence of a singularity, an infinitely dense point at the start of the Big Bang. This suggests that our current physics isn't enough, and we need new ideas. String theory comes into play here, claiming to be a physics model capable of handling gravity and other forces at ultra-high energies. String theory suggests it can explain the earliest moments of the universe. Within this theory, the idea of an erotic universe emerges, suggesting that the familiar Big Bang was not the absolute beginning but part of a larger process. Extending this concept has led to another theory called cyclic cosmology, also inspired by string theory. While the idea of a repeating universe has been around for a long time, string theory provides a strong mathematical foundation for it. The cyclic universe operates in a continuous cycle, moving between big bangs and big crunches, stretching infinitely into the past and future. Renowned physicist Roger Penrose, who received the Nobel Prize in 2020, proposed this theory of cyclic cosmology. He was intrigued by a mathematical connection between the early universe during the Big Bang, characterized by extreme heat, density, and smallness, and the projected future state, expected to be extremely cold, expanded, and devoid of matter. Penrose's groundbreaking theory suggests that these two states become mathematically identical when pushed to their limits. The absence of matter entirely could be the driving force behind the creation of all the matter we observe in the universe. According to this perspective, the Big Bang originates from a nearly imperceptible remnant left after all the matter has been consumed by black holes, which eventually evaporate into lost photons within vast emptiness. So, the entire universe emerges from something that, from another perspective, is essentially close to nothingness. The mystery lies in how this same state can be interpreted as both a cold, empty universe and a hot, dense universe, depending on the viewpoint. The key to understanding this lies in a complex mathematical technique called conformal rescaling, altering the size of an object while preserving its shape. Penrose showed that the cold, empty state and the hot, dense state can be connected through this rescaling, aligning their space-time structures. In conformal cyclic cosmology, the sequence of events unfolds from an old and cold state to a young and hot state. The cold, empty state gives rise to the hot, dense state in a non-causal manner, challenging traditional notions of cause and effect. The concepts involved have metaphysical implications explored extensively by philosophers of science in the context of quantum gravity, where traditional ideas seem to break down. The realms of physics and philosophy intertwine, making it challenging to separate them. Conformal cyclic cosmology offers theoretical models for how our Big Bang originated. Nevertheless, Penrose's theories might not answer a more profound philosophical query about the beginning of physical existence itself. Even if validated by further developments in cosmology, they still prompt reflection on one of the key issues of metaphysics. Why is there something rather than nothing? For the purposes of this conversation, we'll stick to physics-based explanations when examining the origins of these cycles. There are three primary options to take into account. First of all, there's a chance that there isn't even a physical explanation. Second, there may exist an endless sequence of recurring cycles, each of which would symbolize a different world. Each universe's initial quantum state would depend on some feature of the universe that came before it. The last option is a universe that repeats and has a single cycle in which a property of the cycle's end explains how it began. The last two possibilities are interesting because they don't require events to happen without cause, and they give a complete explanation using physics. Penrose suggests a continuous series of new cycles based on his understanding of quantum theory. In quantum mechanics, a physical system exists in many states at the same time until someone observes it and then randomly settles into just one state. Penrose proposes that each cycle is influenced by random quantum events, creating variations between cycles. This idea is exciting for experimental physicists because it opens up the chance to find subtle traces or oddities in the radiation left from the Big Bang, which the Planck satellite has observed. Penrose and his colleagues suggest they might have found traces in the Planck satellite data linking certain patterns to radiation from supermassive black holes in the previous universe. However, some physicists question these findings, and the certainty of their observations is unclear. The recent discoveries by the James Webb Telescope have stirred up the field of cosmology by challenging our current understanding of the universe and potentially casting doubt on the validity of the Big Bang theory. Astronomers have found 6 enormous ancient galaxies, dubbed universe breakers, due to their immense size and age. These galaxies existed when the universe was only 3% of its current age, much earlier than expected for galaxies of such magnitude. According to existing theories, the early universe should have had small, young galaxies during this time. However, these newly discovered galaxies show maturity and size comparable to our Milky Way, creating a puzzling mystery for scientists. The discovery of massive galaxies near the Big Bang challenges what we thought we knew about early galaxy formation. Current models suggest that after a quick expansion, the universe cooled down, allowing gas to come together and collapse, leading to the creation of stars and galaxies during the Dark Ages. However, finding these colossal galaxies hints that the Dark Ages might not have been as inactive as we once thought. Astrophysicist Dr. Emma Chapman of the University of Nottingham said that these results suggest the cosmos had a lot of star formation far earlier than thought. To confirm these findings and determine their consequences for accepted cosmological theories, more observations and thorough research are needed to improve estimates of the galaxy's masses and provide more accurate distance calculations. The study team plans to get spectral photos, and spectral investigation will be essential in confirming these objects' existence and providing more details about their makeup. The surprising nature of these results highlights how scientific knowledge is always changing and how hypotheses must be revised in light of new data. The discovery of these large, old galaxies challenges our existing cosmological framework and demands a reevaluation of our knowledge of the early universe.